Welcome to AIguest. In this comprehensive episode, we will cover the entire first chapter of the Class 10 Insert Mathematics curriculum, dedicated to real numbers. We will dive deep into prime numbers, division properties, divisibility relations, and the beautiful logic behind mathematical proofs. We have structured this lesson into 4 key sections. First, we will explore the fundamental theorem of arithmetic. Second, we will look at HCF and LCM relations. Third, we will solve the classic question about numbers ending in 0. And finally, we will mathematically prove the irrationality of the square root of 2. Let us begin with Section 1. The fundamental theorem of arithmetic is the cornerstone of number theory. Stated simply, it asserts that any positive integer greater than 1 is either a prime itself or can be uniquely factored as a product of prime numbers, regardless of the order of those factors. To visualize this, let's build a factor tree for the number 60. We divide 60 by its smallest prime factor, which is 2, leaving us with 30. Next, we divide 30 by 2, which gives us 15. Both 2's are prime numbers, so those branches end here. Finally, 15 is factored into 3 and 5, which are both prime. We have reached the prime building blocks of 60. By collecting these terminal leaves, we can write 60 as 2 times 2 times 3 times 5, or simply 2 squared times 3 times 5. The fundamental theorem guarantees that this prime representation is unique. Moving on to Section 2. The prime factorizations of integers allow us to easily calculate their highest common factor and least common multiple. More importantly, there is a beautiful relationship between these values for any 2 positive integers. Let's take the numbers 6 and 20. Their prime factorizations are 6 equals 2 to the power of 1 times 3 to the power of 1, and 20 equals 2 squared times 5 to the power of 1. The HCF is the product of the smallest power of each common prime factor. Here the only common factor is 2, and its smallest power is 2 to the power of 1, so the HCF is 2. The LCM is the product of the greatest power of all prime factors involved. This gives us 2 squared times 3 to the power of 1 times 5 to the power of 1, which equals 60. Now let's verify the formula. Multiplying the HCF by the LCM gives 2 times 60, which is 120. Multiplying the original numbers 6 times 20 also gives 120. They are equal. Next, in Section 3, we will address a classic and frequently asked question. Can the number 6 to the power of n, for any natural number n, ever end with the digit 0? For any number to end with the digit 0, it must be divisible by 10. This means that its prime factorization must contain both the prime numbers 2 and 5. However, if we look at the prime factorization of 6 to the power of n, we get 2 times 3 raised to the power of n, which equals 2 to the power of n times 3 to the power of n. As you can see, the only prime factors present are 2 and 3. Since 5 is completely missing, the uniqueness of the fundamental theorem of arithmetic guarantees that 6 to the power of n can never end in the digit 0. Now we arrive at Section 4, the most mathematically elegant part of this chapter, proving that the square root of 2 is irrational. We will show this using the powerful method of contradiction. If the square root of 2 were rational, we could write it as p over q, where p and q are co-prime integers with no common factors. Squaring both sides yields 2 equals p squared over q squared. This simplifies to p squared equals 2 times q squared. This means p squared is even, which forces p itself to be an even number. Since p is even, let's write it as 2 times k. Substituting this gives the quantity 2k squared equals 2q squared. Simplifying this gives 4k squared equals 2q squared, which simplifies further to q squared equals 2k squared. Therefore, q squared is also even, meaning q is even. Here is the contradiction. If both p and q are even, they share a common factor of 2. But we assumed they share no common factors. Since our starting assumption leads to a contradiction, the square root of 2 cannot be rational. It must be irrational. To recap what we have learned today, first, we studied the fundamental theorem of arithmetic. Second, we verified the relationship between HCF and LCM. Third, we proved why 6 to the power of n cannot end in 0. And finally, we walked through the proof of irrationality for the square root of 2. Thank you for spending time with us today at AIguest. If you found this comprehensive breakdown of real numbers helpful, please make sure to subscribe and click the like button. Share this video with your classmates, and we will see you in the next mathematical journey.